Hello and welcome to today's class. So this is going to be the last subtopic under differentiation, and basically we're going to see how we can use the concept of maximum and minimum points that we learned under stationary points to actually solve real life problems. So in this particular problem, we are looking at a situation where a farmer has 100 meters of wire mesh, okay, and he wants to fence a rectangular enclosure. All right, so maybe I'm just going to sketch that out for you so that you see what I'm talking about. So basically we are having a rectangular enclosure. All right, so this is a rectangular piece of land, and so this farmer basically wants to fence this particular piece of land using 100 meters of wire mesh. Okay, so he wants to go all around the perimeter of this piece of land. All right, so the question basically is, what is the greatest area? And the keyword there is area. What is the greatest area he can enclose with the wire mesh? So what is the greatest area that this farmer can actually enclose with the wire mesh given this rectangular piece of land? So basically what we are going to do, we are going to first of all try and express this piece of land using a function. All right, so we know that the farmer has a wire mesh that is 100 meters long. All right, so we are not able really to tell how much of that 100 meters will cover the length of this rectangular enclosure. So we are going to then assume that, let's say that it's going to cover X amount of meters. All right, X meters amount of the wire mesh that he has. All right, and so note that our length therefore will generally assume to be X, and so if our length is X, all right, what then becomes our width? All right, so basically that's a simple question of perimeters. All right, that's a simple question of perimeters. So basically that's going to be 100 minus 2 of x, the two lengths. All right, 100 minus 2x divide by 2, and this should be able to give us the width. So this should give us the width of this particular land. So remember, we are first of all trying to get the dimensions of the rectangular piece of land. Then we can find a way of expressing the area of the whole land using a function from the dimensions that we'll have estimated using algebraic expressions. And so note that this here is basically going to leave us with, when you simplify this algebraic fraction, you're going to be left with 100 divided by 2 will be 50, and negative 2x divided by 2 will be negative x. So this here is going to be the dimension of the width of this particular rectangular piece of land. All right, so it's going to be 50 minus xm, and our length will be expressed as xm. All right, so when you go around this particular piece of land, then we expect that the whole perimeter should add up to 100 meters. All right, but that is not what we are keen on. Remember, the question is, what is the greatest area this particular farmer can fence using the 100 meters of wire mesh that he has? What is the greatest? Basically, we don't know what the greatest area this wire mesh can actually fence this particular piece of land with, but we know, however, that we have an estimated value of, assuming that this wire mesh was accurately used without any wastage, we have the accurate values of what the length should look like, x, and the width should look like. So with this in mind, we can then go ahead and calculate the area of this piece of land given these variables that we have for length and width. So we know very well that area of a rectangular piece of land will always be given by multiplying a length times width. And so we are going to then take our length in this particular rectangular piece of land, which happens to be x, and we are going to multiply it with our width. And our width in this particular case happens to be 50 minus x. All right, so that is what our width is. It happens to be 50 minus x. And so when you multiply this, we are going to then find the function that describes the area of this rectangular field. So we can go ahead and multiply it, or we can just leave it at that. I'll assume I'll let us leave it at that without expanding it, because either way, when we factorize, it still come back the same. So this here is the expression of the area of the rectangular piece of land that we are supposed to fence. All right, so we already have that. However, the question is, what is the greatest area that this farmer can fence with the 100 meters of wire mesh? All right, what is the greatest area? All right, so for us to find the greatest area, we are going to apply the concept of the concept of stationary points. Okay, remember, we are not able to tell the maximum or the minimum point of a function unless we find its derivative and equate it to 0. All right, so for us to find the maxima or the minimum of this particular function, that is area being equal to x into 50 minus x, we are then going to go ahead and basically find the derivative of our area. All right, so we're going to differentiate a, which is the function of our area, with respect to x. Okay, and for us to do this properly, let me just expand this so that it's easier to do. All right, for us to do this properly, maybe I'll expand this so it will be x times 50, so that is 50x. All right, minus x times negative x, giving us x squared. All right, so for us to do this, all right, so of course this is the value of our area. We've just expanded what we had here. For us to find the derivative of a here, then it will mean that we'll take 1, the index of x times 50, which will give us 50. All right, of course, 1 is raised to x is raised to 1, and so 1 minus 1 gives us 0. Therefore, x raised to 0 is 1. So 1 times 50 just basically leaves us with 50. So we don't have an x variable next to 50 there, because it boils down to 1 because of x raised to 0 right there. All right, then so we are going to differentiate the second term, and that is negative x squared. So that's going to be 2 times negative 1, and that's going to give us negative 2. All right, and then we have the index of x here, that is 2 minus 1, giving us 1. So this here is the differentiated function of our area of this particular rectangular piece of land. All right, however, we won't still be able to find the maximum or the minimum amount of wire that was used if we leave it at this point. For us to find the maximum or the minimum length of wire mesh that was used, for us to find the greatest area, that was actually enclosed by this 100-meter wire mesh, then we are then going to equate this to 0 as we did with stationary points. All right, then we are going to find the value at which we're going to find the stationary points, and then use that to solve for this particular problem. And so for us to then go ahead and find the greatest area, we will equate 50 minus 2x to 0. All right, we're going to equate 50 minus 2x to 0 for us to get the stationary points. All right, so basically this is going to give us negative 2x being equal to negative 50. All right, negative 2x being equal to, and so the value of x is 25. The value of x is 25, and so we are finding that the value of x will be 25. That is for the length. All right, so our length here will be 25, and our width will be 25. Will be 50 minus 25. All right, 50 minus 25. That's again 25. If I'm not wrong, basically 25. All right. So our so this is actually a square. This is actually a square. Oh my god, this is I didn't expect to see that. Anyways, so actually it's going to look like a square. If all right, the statement says it's a rectangular enclosure, but we're actually finding out that it's a square. So I really can't tell why. So, anyways, we have found the value of x. And so the value of x here basically is going to give us the maximum area that is actually going to be the greatest area that is going to be enclosed by the wire mesh. And so that is basically going to be, of course, we know that area equals to length times width. And so we have our length as 25, all right? And our width we've also found to be 25. And so the maximum or the greatest area that can be enclosed by the wire mesh will be 25 times 25 meters, which will be 625 squared meters. So that is it. All right. So this is it. But again, we don't know whether this was the maximum or was the greatest area it covered, or the of the smallest area it covered. All right. So if you want to find the nature of this stationary point, you get the second derivative, and if it's a negative number, then it means that that's the maximum. If it's a positive number, it means it's the minimum. So we will find the second derivative of our function, that is a here. So basically, we're going to derive this function that I'm going to label 1 the second time. And so when we find the second derivative of a with respect to x, then notice that these are constant, so it's going to be 0. And so minus negative 2x, when you find the derivative of negative 2x, it's basically negative 2. So that implies that the second derivative of the function of this particular rectangular field is a negative number, and that is therefore a maximum. That is the maximum. That is the greatest. That is the greatest area, maximum area that the wire mesh could have fenced. Maximum area that the wire mesh could have fenced, of course, and we know that that is 625 squared meters. So that is it. That is how we've actually used the concept of stationary points to try and solve a question that requires knowledge of maxima and minima in a simple example. See you in the next video, where I'll be explaining how to solve another problem in the same related, in the same related concept.